All right, so we are concluding our discussion on how to solve systems of linear equations using matrices with our last method, which is called Cramer's rule. And this rule is going to use determinants of matrices. So first we're going to go over what are determinants of matrices, and then we're going to see how to use determinants to solve systems of linear equations. So, first of all, only square matrices have determinants, and recall from last lecture that a matrix is square if it has the same number of rows and columns. So, we denote the determinant of a square matrix A by the symbol dt of A, or like absolute value bars of A. So this notation and this notation, they mean the same thing. We first define the determinant of A for the simplest cases. So if you have a matrix that is a 1 by 1 matrix, then the determinant of that matrix is that one entry that the matrix has. So for example, if your matrix A is just one number 27, then the determinant of A is just 27. Notice that the determinant is a number. So determinant of A is a number. It's not a matrix. Then if we have a 2 by 2 matrix, then the determinant is calculated as follows, and this is something that we went over in the previous lecture. So for a 2 by 2 matrix with entries A, B, C, and D, the determinant is just going to be A times D. So you multiply the entries on this diagonal, and then minus C times B. All right. So for example, if I have the matrix A with entries 1, -2, 3, and 5, what's going to be the determinant of A? So let me write it like that as well, so you guys get used to both notation. So it's just going to be A times D, so 1 times 5, minus B times C. So minus B, which is -2, times C, which is 3. So this is going to be 5 plus 6, and we get 11. Again, notice that the determinant is just a value, a number. What is the determinant of I2? Remember, I2 is the identity matrix with 1s on the diagonal and 0s everywhere else. Well, the determinant of I2 is going to be 1 times 1 minus 0 times 0, and that's just 1. So actually, the determinant of any identity matrix is going to be 1. You can verify that if you want. Now, if I have a 3 by 3 matrix, then the determinant is going to be calculated using what we call a cofactor expansion. And we can do this cofactor expansion by either the first row or the first column, or so basically by any row or by any column. But we'll see that we can choose by what row or column to do the expansion wisely. We'll see in an example. So let's say if I have a general matrix A, a 3 by 3, so that means that the first row, first column coefficient, I can call it A11, the second row in the second column and first row A12, and then A13. Then I can have A21, A22, A23, and then A31, A32, A33. So this is a 3 by 3 matrix with some general entries A11, A12, and so on. So the rule, how do we determine the determinant of matrix A? So if I want to calculate the determinant of A, okay, so this is going to be the rule. I'm going to do the cofactor expansion by the first row. So I'm going to use my first row entries. So the determinant is going to be the first element, so it's going to be A11, times -1 to the power, you take the indices and you add them, so this 1 plus 1. And then it's going to be times the determinant that we obtain from removing row 1 and column 1. So if I remove row 1 and column 1, this is the determinant I am left with. So A22, A23, and then A32 and A33. Because we know how to calculate determinants of a 2 by 2. So if we can reduce this 3 by 3 matrix, not reduce it, if we can find a method that uses 2 by 2 determinants, then we can find a 3 by 3 determinant. So we took care of the first term. Now you go to the second term in the row that you're expanding. So it's going to be plus A12 times negative 1 to the 1 plus 2 now. You're looking at the indices of A12. And then times, if I remove the first row and the second column now, what am I left with? I'm going to be left with this one, that one, and that one. So A21, A31 plus, and then A23, A33. And then I have another element, A13. So plus, let's just say plus A13. So this element, because I'm expanding by the first row, times negative 1 to the 1 plus 3 now. And then if I remove the third column in the first row, I'm going to be left with this submatrix here. So A21, A22, A31, A33. Sorry. All right. So we've reduced our problem of finding a determinant of a 3 by 3 by finding 3 determinants of a 2 by 2, which we have a rule on how to do. So some notation in here. This right here is called a minor. This is called a minor, and this is a minor. And it's actually the A11 minor. So we denote this with M11. The minor 11 is the determinant that is left after removing row 1 in column 1. So when we removed row 1 in column 1, we have the minor left, A22, A23, A32, A33. And that's exactly what that is. This minor right here is M12. And we obtained this one by removing row 1 in column 2. And then this minor right here is M13. And we obtained this one by removing row 1 in column 3. So that's the minors. And then if you include the negative 1 to the 1 plus 1, this whole thing with the minor is going to be called a cofactor. So that's where the name comes from, cofactor expansion. So the cofactor A11 is going to be negative 1 to the 1 plus 1 times the minor M11. And similarly for the other ones. So the minor is just the determinant. The cofactor includes this sign, negative 1 to the 1 plus 1. So the cofactor A11 is just negative 1 to the 1 plus 1 times M11. And the cofactor A12 will be negative 1 to the 1 plus 2 times the minor 1, 2. And the cofactor A13 will be negative 1 to the 1 plus 3 times M13. Sorry. So this is just some terminology that comes with cofactor expansion. So let's look at an example. I am going to squeeze it in here. So let's see my example. If I have the matrix A equals 1, 2, 0, 10, 3, 5, and then 2, negative 1, 3. So if I want to find the determinant of this 3 by 3 matrix, I'm going to use cofactor expansion by the first row. So I'm going to look at the first row, and according to this formula, the determinant of A is going to be the first term, A11, which is just 1, times negative 1 to the 1 plus 1, right, from here, times, okay, the minor 1, 1, 1. So if I remove the first column and the first row, the minor that I have left is this one. So times 3, 5, negative 1, 3. So that took care of the first element. Now the second element, so that's going to be A12, so which is 2 in our case, times negative 1 to the 1 plus 2. So negative 1 to the 1 plus 2 times what's left if I remove the second column and the first row. So the second column and the first row, I'm going to be left with the minor M12, which is 10, 5, and 2, 3. Then the last entry would be 0 times negative 1 to the 1 plus 3 times the minor. But 0 times anything is going to give me 0, so I'm not even going to bother doing that work. So now I can just calculate the determinant. So it's going to be negative 1 squared is just positive 1, times 1 is just 1, times this determinant of 2 by 2. So this is A times D minus B times C. So it's going to be 3 times 3 minus 5 times negative 1 plus 2, negative 1 to the 1 plus 2 is negative 1 to the third, which is negative 1. Negative 1 times 2 is going to be negative 2 times the determinant of this. So it's going to be A times D minus B times C. So 10 times 3 minus 2 times 5. And this is going to give me 9 plus 5. And then minus 2 times 30 minus 10, 20. So this is going to give me 14 minus 40. So it's going to give me negative 26. So notice this is just a number. Okay, so the determinant of a 3 by 3, we're going to use cofactor expansion. Notice that the more zeros I have, the more simplified my answer is going to be. So if you were to choose by what you can expand, choose the row, and we'll see that we can also do it by the column that has most zeros. So for example, so what we did just now, it was expanding by the first row, but we can also expand by any row or any column. And we're going to obtain the same result. So for example, if I have this matrix A, what would be a good row to expand on? Well, it's a row that has the most zeros, so it will be row 2. So we're going to expand by row 2, and then we're going to expand by the third column, and then we're going to see if we get the same result. We have to get the same result. So by the second row, so determinant of A expanded by the second row is going to be, we're looking at the second row, it's going to be the first. So let me put it here again, and I'm going to put this in pencil. 0, 2, 4, and then negative 2, 5, 6. So I'm expanding by the second row. So it's going to be the first element in second row, which is 0, times negative 1 to the, what is the index of this? It's in row 2, column 1, so it'll be to the power 2 plus 1. So this is the row plus the column, times, if I was to remove the second row and the first column, I would just get 3, negative 1, and 5, 6. I didn't have to write this because 0 times anything is going to give me 0 anyway, but I wrote it for practice. And then plus, I'm going to look at the second element in the row, 2 times negative 1. What is the index? This is in row 2, column 2, so it'll be to the power 2 plus 2. And then if I was to remove row 2, column 2, I would have the minor 2, negative 1, negative 2, 6. And then finally, plus the third element, which is 4, times negative 1 to the second row, column 3, so 2 plus 3, times its minor. So if I remove row 2 and column 3, I will have left 2, 3, negative 2, 5. This is the minor. And now I'm ready to find out the determinant. So this is going to be equal to 0. This equals to 0. Negative 1 to the even power is positive, so it's going to be 2 times, let's calculate this determinant. So it's 2 times 6 minus negative 1 times negative 2. So this is just from this. And then plus 4, negative 1 to the 5th power is negative 1. Negative 1 times 4 is negative 4. So negative 4 times the determinant of this minor. So 2 times 5, which is 10, minus negative 2 times 3, it will be 10 plus 6. So then this will give us 2 times 12 minus a plus, but a minus in between, so minus 2, minus 4 times 16. So 2 times 10 minus 64, that's 20 minus 64, negative 44. So expanding by the second row, it came down to finding these two cofactors multiplied by the respective entry in row 2. So now let's see, expanding by the third column. So my determinant A, I'm going to expand 2, 0, negative 2, 3, 2, 5, and then I'm going to expand by the third column, which is negative 1, 4, and 6. Okay, so I'm expanding by the third column, so I'm going to use this element, negative 1, times negative 1 to the index that this has. It's row 1 in column 3, so it's going to be negative 1 to the 1 plus 3. So notice here, I always have negative 1 times the number of row plus the number of column, but this happens that also the entry is negative 1. So that's why there's a negative 1 here as well, times the minor. So if I remove row 1, column 3, the minor left is 0, 2, negative 2, 5. Now plus, I'm going to go to the second element, which is 4. So 4 times negative 1, what is the index for 4? It's going to be row 2, column 3. So 2 plus 3 times the minor. So if I was to remove row 2, column 3, because I'm looking at this element that is in row 2 and column 3. So if I remove the row and the column, I have left 2, 3, negative 2, 5. And then plus finally the last element in the column that we're expanding, 6 times negative 1 to the 6 is on the third row and third column. So it's going to be 3 plus 3 times, if we were to remove the third row and third column, we would have left 2, 3, 0, 2 for the minor. And there you go. Let's find out what this is. So it's going to be negative 1 to the fourth, that's positive 1, but there's a negative in front, so it's going to be negative. 0 times 5 is 0, minus 2 times negative 2, plus negative 1 to the 2 plus 3 is negative, times 4, so it'll be negative 4, times the determinant of this 2 by 2, so 2 times 5, which is 10, minus 3 times negative 2, plus negative 1 to the 6th power is positive, and then 2 times 2 is 4, minus 3 times 0 is 0. So this should give us negative 2 times negative 2 is positive 4, minus 4 times 10 plus 6 plus 24, minus 4 minus 64 plus 24. So this is 20 minus 64, which is also negative 44. Which is good because that's what we got by doing expansion with the second row. So it doesn't matter what you pick to expand. Are you going to expand by the second row or the third column? But which one was less work? The second row, the one that had a 0 in here, was less work because we have a 0. So we only have to evaluate 2 minors. Compared to the third column, didn't have any 0, so we had to evaluate all 3 of them. So this one would be best to evaluate, to expand by the second row, or this first column because the first column also has a 0. So this is how we find determinants. Next, we'll see how to use determinants to solve systems of linear equations.